These are called Friedman numbers. It can be written in a non-trivial way, just using the digits itself together with any combination of your usual mathematical signatures: plus, minus, times, divide. You can even raise things to a power, and you can use some combination of brackets if necessary. So 25 is a Friedman number. Okay, why is 25 a Friedman number? Because it can be written in terms of the two digits that make it up as 5 to the power 2. So I've just used the raising power operator to do that. 121, same sort of idea. The two ones form 11, and I raise it to the power 2, and I've got 121.
Immediately I'm saying this could be described as recreational mathematics.
It's the kind of thing I used to have great fun playing with, but actually there's some really neat things you can do with it. The brackets you've got to be a little bit careful with. You're not allowed just to simply wrap one number up in a bracket. So 125 is 5 to the power of 2 plus 1. So I'm just using the brackets there to add the 2 and the 1 and make up 3, so 5 cubed is 125. Well, if I wanted to go for one, say, with 4 digits, then 9261 is 21 to the power of 9 minus 6. So there's actually 72 of these numbers with 4 or less digits. And there's a really nice sort of subset of them. 14 of these are known as nice Friedman numbers. Well, a nice Friedman number is where the order of the digits remains the same. So a simple one is 127. 127 is made up of minus 1 plus 2 to the power 7. The order of the digits, 1, 2, 7, is the same as appears on the right-hand side. Whereas if I say took 125, the left-hand side is 1, 2, 5, but the right-hand side is 5, 2, 1, or 5, 1, 2.
Is that not nice?
Not formally nice. It's for many of us, we quite enjoy 125. It's got many nice properties, but on this occasion it's not a nice number, not a nice Friedman number anyway. So you could do, I mean, if I want to just get a bit bigger, it's 343, for example, is just made up of 3 plus 4 to the power 3. Or I could get a bit bigger, and 6455 is made up of 6 to the power 4 minus 5, all times 5. So you get the idea that you can make up various combinations, and in fact we've already come across a class of these, vampire numbers, that we've done videos with. So vampire numbers are made up of these where you, instead of using all the various combinations, we're just using the multiplications. So vampire numbers are an example. So 1260 is a vampire number, but it's also a Friedman number because it's 21 times 60. You know, you can get a bit bigger. So we've got 5-digit numbers, of which there are 272 of them, by the way. 10192, which is 101 to the power 2 minus 9. And if I went to a 10-digit one, 832619750, what's that equal to? 91,248 to the power of 5 minus 3 plus 0 times 67.
Is the 0 times 67 together? Have they just used the 0 there to cheat away?
Well, the 0's in here.
All right.
And so it's part of it. But what it does make it, there is an interesting caveat which I should have mentioned. You can't have leading zeros, they're not allowed. For example, something like 001729 and write that as 1700 plus 29. I'm not allowed to have the leading zeros in there in that definition. But there are some neat ones. There's some even more.
Better than this even?
Oh, it gets better. What's the smallest number smallest Friedman number that I can make up with just repeating the same digit?
These are called rep digits, aren't
Rep digits. Rep digits, okay? And the smallest is 1, 2, 3. These are all 9s. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And it's made up of 9 plus 9 over 9 to the power of 9 minus 9 over 9 minus 9 over 9. How about ones? So now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that is equal, if I've got my algebra right, 11 minus 1 to the power of 11 minus 1 times 1 divided by 11 minus 1 minus 1. So they've got the same number on the right hand side.
Why are you laughing?
Because it's just cool. But I haven't finished.
There's more.
There's more.
Right.
How about if I ask the following? There's a set of numbers called your pan-digital.
We have covered pan-digital numbers.
Oh, you've done? Yeah, okay. Well, but you haven't done pan-digital Friedman numbers, I bet. Here's one, right? So a pan-digital number is the one that includes all the numbers in any given base. So if I say 1, 2, 3, 4, 5, 6, 7, 8, 9, well, I can write that as a Friedman number because that's equal to, I think I need two brackets, 86 plus 2 times 7 to the power 5 minus 91, all divided by 3 to the power 4. So that's one pan-digital number. We can do another one. 9, 8, 7, 6, 5, 4, 3, 2, 1, right? And this is 8 times 97 plus 6 over 2 to the power 5 plus 1, again divided by 3 to the power 4. So you might say, is it easy to get a nice pan-digital number? And indeed, they're there, but they're not that easy to get. There is one here, 2, 6, 8, 4, 3, 5, 1, 7, 9. And that is equal to, remember, what's nice about it is the order remains the same. The order of the numbers remains the same. So it's minus 268 plus 4 to the power of 3 times 5 minus 1 to the power 7 minus 9. And that will give you back your original number. It turns out, as the number of digits and the number increases, the likelihood of it being a Friedman number also increases. If there are f of n Friedman numbers less than any given number n, then it turns out, and I don't know the proof of this, I haven't been through it, that as n increases, the ratio of f of n over n tends to 1. In other words, the likelihood of finding a number tends to unit. So given a distribution of numbers, of larger n, then you pick a number at random, then the likelihood is that it's actually a Friedman number.
So the higher we go in the number line, the more dense it becomes with Friedman numbers.
Yeah, I think that's right.